it may seem a little unusual that you're listening to an astrophysicist, a rocket scientist, talking about sustainability. What can I teach anybody about sustainability, other than recycling in an astrophysical context? And some of my colleagues would argue that some of my publications might be worthy of recycling as well. But really what I want to do is help you make connections. Science and learning is all about connecting the seemingly disconnected. And we all do this. We're all scientists with a capital, with lowercase s. I'm one with a capital S because I get paid for it. But science is a process that we all undertake. And basically making those connections, those eureka moments, people maybe oversimplify the process of scientific discovery as a series of brilliant eureka moments. But in fact, science and learning is a series of tiny eureka moments. And you don't have to be a research scientist to have those. Just learning about something. I heard from the science editor of The Economist magazine a couple of months ago about a new theory of why zebras, as he would pronounce it, have stripes. And it was a very interesting theory, and I must admit, I was kind of embarrassed that I had never actually thought as a scientist of why do zebras have stripes in terms of an evolutionary biological context. And so that was a eureka moment for me. It wasn't something that I discovered that nobody else in the world knew, but it was something that I discovered that I had never known before or thought about. And now it's making me think more carefully when I observe. Well, here's an image of one of the largest clusters of galaxies. Each one of these galaxies is a city of stars, city limits that spread out across more than 100,000 light years and populations of hundreds of billions of stars. And the reason I'm showing you this image is because I came across an image recently that I thought was an unusual elliptical galaxy, like you might find here in the Virgo cluster, or some strange malformed globular cluster. Let's take a zoom in on it. Turns out this isn't a galaxy or a star cluster. This is a photograph by an art photographer, Mandy Barker, of plastic debris that has been scooped out. We're talking about condensed water and cans of soup. This is debris that's suspended in the sea that's been taken from what's now known, unfortunately, as the Great Pacific Garbage Patch in the North Pacific Gyre, stretching across hundreds of kilometers of the North Pacific, a floating junkyard. And this prompted me to learn more about what's going on there. And I was unaware of a lot of aspects of this. And the whole reason that I looked into it was because I saw this image. And I think maybe that's what Mandy Barker had in mind. It's rather unsettling because she's put together what are undeniably beautiful images, which kind of have a cosmic astronomical feel to them in many cases, but of something which is very, very disturbing and ugly ultimately. So the reason I'm here really is to help you make connections. And in fact, Jacob Bronowski himself promoted that point of view. Here's a quote: "We receive experience from nature in a series of messages. From these messages, we extract a content of information. That is, we decode the messages in some way. And from this code of information, we then make a basic vocabulary of concepts and a grammar of laws, which jointly describe the inner organization that nature translates into the happenings and appearances we meet." And that is the process of science and learning. And so we're all looking for patterns around us and trying to interpret those patterns. And humans are exceptionally good at finding patterns. One of the things in which we probably still outrank computer software, although I'm looking over my shoulder at IBM's Jeopardy champion Watson. It's very good at connecting patterns between words and numbers and a response for answers to give in the form of questions. But humans are so good at finding patterns, we even find patterns where there aren't any patterns. Here's a patch of the sky, a fairly broad patch of the sky, and in this patch of the sky, you are seeing the mighty warrior Perseus and his winged steed Pegasus and the beautiful princess Andromeda. And in case you're having some trouble following, here, let me guide your eye. There you go. So now it should just leap right out. It's pretty obvious. Personally, I'm convinced that the first people to name the constellations were also the first people to ferment wine and experiment with mushrooms, because I don't see those things up there. But I did, last night, did see a pattern in here which I had never seen before. Let me share with you a new constellation, literally a new constellation, in honor of the 50th anniversary. Well, the reason I've chosen this patch of the sky wasn't just at random. At the center of this image, rather innocuously, not a particularly bright star that would draw your attention, that star is noteworthy. It's a star like the sun, almost a twin to our sun. And it's one of the first stars known to have a planet orbiting around it. The star is called 51 Pegasi, and when we found a planet around it, it became 51 Pegasi A, and the planet is 51 Pegasi B. We're not very good at naming planets, unfortunately, not very romantic, but still, this was a very exciting discovery, and we live in an exciting era, and I hope to share some of that with you. Speaking of planets, we now have a sample, and I'll give you some of the statistics shortly, of planets beyond what we knew only a short time ago. So here's a planet, and I know that there are some other fellow uber astro geeks out there. Can anybody identify this planet for me? I'll give you a hint. This is not a visible image, it's an infrared picture. Turns out to be the Earth, seen in infrared light from space. And that gives us a different perspective. The Earth almost seems like an alien world in appearance. And at those ranges of energies of light, and at the physical processes that we're exploring, in some ways it is alien to us in our everyday lives. And the reason that I'm sharing that with you is because we're going to look outward to be able to look back inward to see the Earth in a different perspective. And it's appropriate. Carl Sagan had that approach. He was the one who came up with the idea to take instruments on the Galileo space probe en route to Jupiter, swinging by the Earth in order to get a kind of a gravitational boost to head to the outer solar system, to take those instruments and point them at the Earth and pretend to be aliens. Say, we're looking at the Earth for the first time, we're looking for evidence of life. Would our instruments tell us that there's life on Earth, other than the glow of the artificial lighting of the cities on the dark side of the planet, and other than the screeching of Don Cherry and Howard Stern on radio and television wavelengths? And so it is really important, I think, for us to look at our own planet from different perspectives and obviously at different wavelengths. So I come back to, what can an astrophysicist teach you about sustainability? The lessons begin. I have a curriculum. Lesson 1 is in the course Astro Marketing 101, brand power. We all know that a logo is an important pattern for us that we associate with products and services. And if we see that, we know immediately what we're getting, whether we will like it or not. And here's a very popular logo in my neighborhood in Kitsilano in Vancouver. This would be more my style of logo, although I choose not to have a car. But if I had one, it probably would be an old Volkswagen, I suspect. But here's another logo. I would argue that this is maybe one of the most important logos for the environmental movement since it began. The image of the Earth from space. Here's a better version of that logo. The realization that's seeped into the public consciousness that the Earth is this tiny blue marble in the blackness of space, that it doesn't go on forever, that it isn't limitless, even though it seems that way to us as human individuals. And so I think that awareness is maybe one of the most important tools that has brought forward the environmental movement. Here's a real image. This looks like something from a science fiction movie, but this was taken by the Japanese lunar orbiter, Cayuga, which was renamed Selene, orbiting above the moon, and got this beautiful image of the Earth above the lunar horizon, and there's a nearly quarter Earth as seen from Cayuga, Selene. Also in astro-marketing, not only a logo, you need a good, concise message or slogan. The people that are in charge of tourism at Las Vegas know this. They came up with "What happens in Vegas stays in Vegas." I'd like to propose a slogan: "What happens on Venus stays on Venus, but could happen here." And that brings me to lesson 3, the field of astroforensics. And in any detective work, you often find clues in unexpected places. Let me take you back to a mystery in astrophysics and planetary sciences. Here is basically the average temperatures of the planets in our solar system and the recently demoted dwarf planet Pluto in our solar system, and the sun. And I've highlighted here the fact Mercury, the closest planet to the sun, and Venus, the second closest. And Venus is actually hotter, even though it's further away from the source of light and heat. And this was a surprise when it was first measured. Until the 1960s, in fact, scientists would have treated the possibility of life on Venus very seriously, even more so than the possibility of life on Mars. It was confirmed, the mystery was confirmed by a spacecraft, Mariner 2, which flew past Venus and said, yes, undeniably, this is a hot planet. This is the detective that solved the mystery, even before that confirmation. The university PhD student, Carl Sagan, there's his yearbook picture, published a paper called The Surface Temperature of Venus in 1960, using what he later recalled as embarrassingly crude methods, and he took data from tables that were meant for engineers to design steam boilers. And what he demonstrated was that the planet Venus could be a greenhouse, a planetary greenhouse, a global furnace. And this had to have been, I think, a little bit of bittersweet, because it was a great accomplishment. But at the same time, he basically destroyed probably one of his boyhood dreams as a science fiction fan. He dreamed of a living sister world with swamps and oceans. And he had to admit to himself that Venus is a hot, dry, sandy, and probably lifeless planet. But because of that recognition, Carl Sagan realized that, hey, that's the Earth's sister world. Not that much different than here, not that much closer to the sun than here. Could it happen here? And he raised the alarm, starting in the 1960s and through the 80s, before anybody was really seriously talking with the buzzwords of greenhouse effect and climate change. He was ahead of his time, and like many who were ahead of his time, he was labeled a wacko in this particular case, an extremist. People didn't take this seriously. In fact, to the extent that in 1990, Saturday Night Live made fun of him with almost an entire episode dedicated to the Carl Sagan's Global Warming's Christmas special, where our own Canadian Mike Myers played Carl Sagan and Tom Hanks played guest Dean Martin. You know you've hit the zeitgeist when Saturday Night Live is making fun of you, but basically, we might not be having the same kind of conversations that we're having today about climate, about changes and so on, had it not been for astronomers trying to understand why another planet was so hot. And if it had not been for a young astronomy student who had shown why it was so hot, and that's the kind of process that can happen on an Earth-like world. And hey, we live in an Earth-like world. So here is a plot of the temperatures of the atmospheres of Earth and Venus as a function of altitude, going up to above 100 kilometers above the surface, temperatures in Celsius. You can see that Venus veers off dramatically from the Earth. Those are, speaking of the Christmas special, those are the ghosts of Venus past and present. And Carl Sagan was one of the first to alert us to the possibility that could be the ghost of Earth future. And that's why we're having this important conversation today as a society. Now, when you hear the words greenhouse gases and global warming, those are now like four-letter words. Those are bad words. But they're not really bad words. Remember, I showed you that infrared image of the Earth, contrasting it with what you would see by eye from space. The reason it looks so different is because of the water vapor in our atmosphere. It's opaque, almost totally opaque to infrared wavelengths of light. So infrared light has a hard time to escape. It turns out water vapor is the most dominant greenhouse gas in the Earth's atmosphere. And we should be grateful that there is something called the greenhouse effect and that there are greenhouse gases like water vapor, because if it weren't for that, we likely wouldn't be here. Maybe there would be life on this planet, but I can almost guarantee that it wouldn't be life as we are experiencing it today, because the insulating effect of water vapor as a greenhouse gas has basically raised the Earth's average temperature to a livable level. And without the greenhouse effect, even with an atmosphere, and even with what would be a livable atmosphere, the average surface temperature on this world would be 17 degrees below Celsius. You know, and that's including like tropical climes. So I go back to that image of the part of the sky with Perseus and Pegasus and Andromeda, and that star that harbors an exoplanet. That's the term that we use for any planet orbiting a star other than the sun. And lesson 4 is, why should anyone care about exoplanets? You know, that star is about 50 light years away from us. Who cares if there's a planet orbiting a star 50 light years away? And why bother even looking? Some people have suggested that the reason we should be looking for other planets is to find an environmental emergency escape route. If we screw things up here, we can move there. And in fact, somebody as prestigious as Stephen Hawking has actually made that case several times, including on his 70th birthday. The survival of the human race is at risk as long as it's confined to one planet. Once we spread into space, our future should be safe. So, could we move to the stars? Could we evacuate in the event of an environmental catastrophe here? Our nearest neighboring star is a dim red dwarf star called Proxima Centauri, not visible to the unaided eye without a telescope, not visible from the northern hemisphere from here. And we don't know if it has any planets around it, but let's, for the sake of argument, say that there is a planet orbiting it on which human life could thrive. So we wanted to move there. First step in making any trip is to consult a map or make a map from the Earth to Proxima Centauri. So here's a map of Toronto. Here's where we are. Here's a map of where we are in the solar system on the third planet orbiting the sun. The scale of that map is the distance, the average distance between the sun and the Earth, 150 million kilometers. It takes light a little over 8 minutes to travel that distance, even traveling at 300,000 kilometers per second. It still takes 8 minutes for light to get to us. So when you're looking at the sun, don't stare at it directly. You're seeing sunlight. You're seeing the sun as it appeared 8 minutes ago. If the sun were to wink out right now, and I can assure you as a stellar astrophysicist that's not going to happen, but if it did, we wouldn't know about it for 8 minutes. So forget about living every day as if it's your last. Live every 8 minutes as if it's your last. So let's zoom back in to Toronto, and let's zoom in even further to the University of Toronto campus, and to 45 Wilcox Street, and to the William Dew Auditorium. And we heard from Dorion about the airport security. Apparently, University of Toronto security is very high too, because they tried to get a floor plan of this auditorium, but that is classified information. So I had to kind of fake a floor plan. So here's the floor plan. It's not quite. It's actually surprisingly similar. I'm better than I thought to how things are laid out. And what I want to do is basically in our mind's eye do what Einstein would call a Gedanken, a thought experiment. something which is difficult to do in a practical sense, but you could imagine doing and could see what the results are. And the thought experiment I want to do is to make a map. We're going to lay out a big piece of paper here on the floor of the auditorium and over the chairs, and it's going to be our map of our local part of the galaxy, our Milky Way galactic stellar city. And two of you sitting there, any two of you who are about a meter apart, that will be the scale of our map, that the sun and the earth would be about a meter apart. And remember, every meter in reality is 150 million kilometers, so we're shrinking down the universe by a factor of 150 billion times to try to fit things onto our piece of paper in this room. And now what I want to do is, on this map, I want to put our nearest neighboring star beyond the sun. Problem is, we need a bigger map, a bigger piece of paper. So, let's go to the map of the campus. Well, it turns out we're going to need a bigger map. Toronto. Toronto's a big city. Bigger map. Let's try Southern Ontario. I was born in Chatham, now known as Chatham-Kent, but I stubbornly refuse to rename it. It's Chatham to me. And there's Chatham. And basically on our map, the nearest star would be beyond Chatham, closer to Tilbury in Southern Ontario, at a distance of about 300 kilometers. This is the size of the piece of paper we would need for our map. And every meter on that piece of paper represents 150 million kilometers. It takes light 8.2 minutes to travel every meter. It takes our space probes currently on the order of a year to travel that meter. Imagine what it would be like to walk from Toronto to Chatham at the rate of a meter per year. That's why we haven't even tried to send space probes deliberately targeting to other stars. And so if we were driving there, it's a very long drive. And there is a very tight speed limit. For a while, it looked like physicists at the CERN Accelerator Lab might have found a way to break that law slightly, but that turns out to have been an error in the experiment. And the speed limit really is just over 1 billion kilometers per hour. And at 1 billion kilometers per hour, it still takes 4 years to go to our nearest neighboring star. So on the 401, if you were traveling at a meter per year, it's a long trip. Now maybe we'll find a way to exceed the speed of light, and Albert can get a lift on board the Spaceballs Winnebago, but we're not there yet. So when Stephen Hawking gives the impression that astronomers are finding planets because we're finding a possible new home for humanity, our technical capability of, one, screwing up this place, and two, responding to the natural changes and cycles that happen on our planet and to our sun, is far less advanced, it's far more advanced than our ability to go anywhere else. We're not going anywhere very soon. So I can confidently say Stephen Hawking is wrong. I love saying that. That brings me to lesson 3 again, astroforensics, finding clues in unexpected places, sometimes very, very, very distant places. And it opens up a new field of astroecology, in which these remote suns and planets teach us about our own sun and our own home planet. Let me put things in perspective. Go back to the 7th of January, 1610. There were only 6 planets known to humanity. The 5 wandering stars in the night sky that you could see without the aid of a telescope: Mercury, Venus, Mars, Jupiter, and Saturn. And the 1 planet that you could see without a telescope by looking down, the one on which we live. And the reason I picked the 7th of January, 1610, is because that's the first night that Galileo Galilei used the simple telescopes to look at one of those wandering stars, Jupiter, to discover that it wasn't just a pinpoint of light, it was a globe, it was a world, it was really another place. And not only that, it was a world that was being orbited by moons. that we now refer to as the Galilean moons. These are his observations. It's kind of like his version of a science fair project, showing the moons looking like tiny stars. His sponsor, his research, was being sponsored by the rich Italian Medici family, and he wanted to call these the Medician moons. He knew on what side of the bread his butter was on, but that never caught on. We call them the Galilean moons, the 4 largest moons of Jupiter. And now we're in the era of telescopes. And so now we've got telescopes. We can look up in the sky, lots of discoveries. In essentially 418 years in the era of telescopes, we added 3 to the tally of known planets. And to be honest, we actually only added 2 because we nasty astronomers demoted Pluto a few years ago to the status of a dwarf planet. So like more than 4 centuries of the era of telescopic astronomy, and we could only really increase the number of known planets by 30%. Let's see what's happened in the last 20 years. As of this evening, just before I ran across Wilcox Street to come here, 763 confirmed planets and 2,300 candidate systems. And here is a map of our neighborhood in the galactic city, showing, in fact, that scale there, 50 light years, is the distance between the Sun and 51 Pegasi, sun-like star that harbors a planet. And so we live in an era of revolution. It's actually kind of appropriate. The reason we say revolution in the sense of overturning of attitudes and political and social change is because of Copernicus's book, De Revolutionibus. Revolutions just meant orbits, moving around in circles. And now, because of the impact of Copernicus and Galileo, revolution has taken on a much broader significance. And I'm personally convinced that 400 years from now, if there are textbooks, students, professors, universities, people, that they will look back at this time, this decade and the decade to come, this century without a doubt, in the same way that we look back at the time of Galileo. The revolution in our cosmic view is just as profound. We're just too close to it, and the information gets disseminated much more quickly than it ever did before. I'm guilty of doing that. Now, in the days when there were really only 6 planets or even 9 planets, and there wasn't very much computing power, or there weren't computers, you could reproduce the motions of the planets with clockwork mechanisms called orreries, named after the English Earl of Orrery. Let me show you the era in which we live today. Clockwork mechanisms just don't cut it. Here is what we call the Kepler orrery. It's put together by my friend and colleague Dan Fabrici, who's now at the University of, or going to the University of Chicago. And these are just some of the planets that we have found, candidate planets. The stars aren't showing up in here because they're just at the center. And the sizes of the planets are to the relative scale and mass, but not things. But the orbital periods and the orbital sizes are all in proportion. We can zoom in on a bunch of multiple planet systems that are just as complex as our own solar system. And so this is the modern version of an orrery, and even it doesn't do it. This is just a handful of the 2,300 candidates that we have in hand, of which I would say about 80% will stand the test of time. Now, the easiest things to find are the biggest, the most massive. And so not surprisingly, the early discoveries were of things that were like Jupiter, the most massive planet in our own solar system, a gas giant. And here are some of the ones discovered by the NASA Kepler mission. I'll come back to that in a moment. And as we've gotten better over time, we've gotten to smaller and smaller worlds, starting to get down to things that approach the size of the Earth, things that we call SuperEarths. And only a few months ago, we announced the first detection of planets that were actually the size of the Earth. In fact, a planet that's even slightly smaller than the Earth and Venus, our sister world, Kepler 20e and Kepler 20f. Again, technically accomplished, but when it comes to naming things, we have a lot to learn. Now, there are planets that are in what we call the habitable zone, in which the surface temperature of that planet could be between the freezing and boiling point of water. And as Dorion pointed out, it might be, it's a matter of which came first, the chicken or the egg, or the chicken soup and the egg drops. But the point is for life as we know it, as a solvent, you need water, whether it was the life that made the water possible, and our best mechanism for bringing water to the surface of the Earth now, we believe, were the impacts of comets and icy Kuiper belt objects that were kind of deflected into the inner solar system. So the kinds of things that might have wiped out the dinosaurs probably did, and might eventually lead to another future extinction event, were also probably responsible for us being here to bring the water. But the planets, many of the planets that we found in the habitable zones are gas giants, like Jupiter, not the kind of place where you normally think about life. But wait, Jupiter has those Galilean moons. They're like worlds in their own right. The largest of them, Ganymede, is larger than the planet Mercury. If it were revolving around the sun, it would be a respectable planet. And so if you've got a gas giant that's in the habitable zone, the Goldilocks zone, where the temperature isn't too cold or too hot, it's just right for liquid water, and one of the what we would consider necessary but if not sufficient conditions for life, then those moons could harbor life. In fact, in the movie Avatar, the planet Pandora is actually a moon of a gas giant that's in the habitable zone of its star. And in our own solar system, Europa, one of those 4 moons, now the evidence points to the fact that beneath its icy crust there may be a deep liquid water ocean, and a warm ocean. And so there could be life. When we look at the crust, we see evidence for cracks, for things that are almost like icy continental drift and glaciers. And through those cracks, some of that liquid water could emerge to the surface and refreeze. And so now many planetary scientists and exobiologists would maybe argue that rather than Mars being the most likely place to find other life in our solar system, that Europa or one of the moons of Saturn and Enceladus are maybe even more likely abodes for life. But what about Jupiter itself? Well, I talked about making connections between the seemingly disconnected. Here's an equation. Carl Sagan plus Jupiter plus Isabella Rossellini plus porno plus the Toronto International Film Festival plus Jaymie Matthews plus exobiology. What does it lead to? I'll give you a few minutes to work on that. Well, you don't necessarily have to think about life on a moon of a gas giant planet like Jupiter. Somebody actually thought about life in a gas giant like Jupiter. Carl Sagan, in his Cosmos series, speculated on at a deep enough layer in the atmosphere of Jupiter where the temperature is high enough and the pressure is just in the right range that maybe you could have life. There's no solid surface, so life would kind of have to float. And there was one category of creatures in his supposition called floaters. And there were hunters that flew around and were gliders. And there were, inevitably, sinkers as well. And I remembered this. This was one of the things in the Cosmos series that stuck with me. And Isabella Rossellini approached me and a number of other scientists a couple of years ago to help her unveil something at the Toronto International Film Festival and at the Royal Ontario Museum here in Toronto. Because Isabella Rossellini is a green person in mentality. She's interested in the environment. She also has an empathy with animals. She lives in New York. She loves going to the zoo, and she watches the animals, and she can mimic their behavior and kind of anthropomorphize it. And so she wanted to teach people about animal and insect reproduction. But if you have a series, and this is on the Sundance channel, Robert Redford's channel, if you have a series that's called Animal and Insect Reproduction, you can bet what the ratings are going to be like. So you thought, well, how will we lure in viewers? Well, let's just call it green porno. And she writes and stars in them as the creatures, and so this is an episode on snail sex. And there's another one on, I can't remember if that's fruit fly sex or not, but And there are some other even more explicit things. It's kind of like, Sesame Street meets South Park meets The Ascent of Man. So Isabella Rossellini asked a number of scientists, including me, to help at the red carpet debut of the third season of Green Porno, and the task was, each of us was to design and build and then model on the red carpet a reproductive organ, a penis hat. And a planet that we had recently discovered and were studying, a gas giant. I thought, okay, I'll come up with a life that could live in the atmosphere of a gas giant. And I was inspired by Carl Sagan's hunters and floaters and hunters and sinkers. And so there's a connection. Carl Sagan inspired me. Isabella Rossellini gave me the excuse. And here is the creature which I called interstellar Rossellini. And basically this is a species. It's a little bit like a bee colony, except it's the male that's largely dedicated to reproduction. It might sound familiar to those of us knowing human society. And basically all it does is float around, and in its body it generates semen, and then females, who are the active ones, latch on to one of its 8 members, and then it starts to use its weak muscles to spin, to control its own internal angular momentum. And it's like a tilt-a-whirl ride. And it's the centripetal acceleration that forces the seed to impregnate the females. And then once they're impregnated, they detach, fly off, and do productive things. And then the male basically slows down and spends time building up another supply of seed for the next riders to get a ticket on the tilt-a-whirl. And here I am at the red carpet ceremony.
Of the tilt-a-whirl. He starts spinning like this. And the centripetal acceleration, the centrifuge effect, drives the seed, the sperm that's created here in the brain, to impregnate the females. That there are 6 riders of the tilt-a-whirl.
So that's exobiology in action. So the equation, Carl Sagan, the Cosmos series, which planted that seed in my mind. Jupiter, his speculations on the possibility of alien life on a gas giant planet, just not on a planet with a solid surface. Isabella Rossellini's empathy for animal life and insect life. Green Porno, the debut of the third season at the International Film Festival of the ROM. My willingness to do anything in public, and the discovery of exo-Jupiters, and that's what all led to interstellar Rossellini. And so this is an example. This is literally how science works and how inspiration works. Now there are planets with what we believe have solid surfaces that are in the habitable zones of their star, and the first one we announced during the first Kepler Science Conference back in December, Kepler 22, and here it is. The green zone represents the habitable zone, the Goldilocks zone, and it's compared to the inner part of our solar system, the orbits of Mercury, Venus, the Earth, and Mars, and the habitable, the same scale there. So this is a super-Earth. This isn't quite an Earth. There aren't any Earth-sized planets, confirmed Earth-sized planets yet, that are in the habitable zone, but just stay tuned. So I go back to my question, though, still, although it's fun and I get to meet celebrities at film festivals, why am I looking for other planets? It's better to know our planet, the Earth, to study the Earth in context. If we really want to understand our planet, we have to have other examples. If I were an alien anthropologist wanting to understand human beings, I could learn a lot by just studying one human being and interviewing her and doing simple non-invasive tests. But I would miss out on an entire gender. I would only know of a human at a certain age who was raised in a certain part of this planet under certain conditions. In order to really understand the human species, you have to be able to study a very large sample of human beings. In order to be able to understand Earth-like planets, specifically the Earth, we have to study a very large sample of planets and put it in context. So how do you look? Well, the most intuitive thing would be to take a picture. Could we photograph another Earth around another star? We've got big telescopes, big light buckets, as astronomers would call them, with the CCD digital imagers. You'd think, okay, we should be able to do that. The problem is that planets are faint. Even from within our own solar system, without a telescope, there's only 5 of them that we can see. And even when the Voyager 1 space probe, on its way being flung out of the plane of our solar system, looked back at a distance from only 20 astronomical units, 20 times further from the sun than we are, it took a snapshot of the Earth. And that's it, from a distance of 300 billion kilometers. The first Jacob Bronowski lecturer labeled this the pale blue dot. And if I go back to my lesson in brand power, I said this was an environmental awareness logo. Here's an even better environmental awareness logo, the pale blue dot. We got to have a campaign around this. We got to have pale blue dot tattoos, bracelets. I mean, basically, if anything is going to remind us that the Earth is tiny and that the resources are limited in the big picture, it's that image of the pale blue dot. Now imagine trying to take a snapshot of the Earth from the distance of one of the nearest stars, 1.5 billion times further away than Voyager 1 was, 90 million billion kilometers. That's a challenge. Planets are faint. Lighthouses, like these here in Vancouver, are bright, relatively speaking, certainly compared to flashlights. Imagine that you are staring into the beacon of a lighthouse. The lighthouse keeper has left a flashlight on the shelf there. But looking at a sun from afar, that sun is 1 billion times brighter than any Earth hidden in its glare, like that flashlight, which we can only see because we turned off the lighthouse beacon. We can't turn off stars, probably a good thing, but basically it's very difficult to see an Earth in the glare of its parent star. So we can't photograph an alien Earth, not yet. Someday, and someday probably not in the too distant future, but not yet. So I go back to my question again, how do you find an alien world? Well, the principle is the fact that stars and planets aren't nailed down in space. They're not tacked in space. And as the Earth orbits the sun, they're feeling a mutual gravitational attraction. The Earth is pulling on the sun with the same force that the sun is pulling on the Earth. It's just that the Earth is not very massive compared to the sun. So as the Earth moves in its large orbit, the sun is also forced to move in response. And so basically, the sun, the planets, and stars are square dancing. Those stars and planets are spherical, and the orbits are ellipses, sometimes circles, but they're square dancers. Like these two girls. Or this boy and his slightly younger sister. Or this father with his baby son. Well, the reason why I'm showing you these is because this is basically the principle of how stars and planets orbit each other. These two girls dancing are a binary system. Their arms locked in place are doing the job of gravity. They have about the same weight, like two stars with the same mass, orbiting a common point equidistant between them. The little boy is a bit heavier than the girl, and so the balance point between them is closer to the heavier boy and closer to the heavier star. And the father and the baby dancing, the dad is way heavier. And now we're into the realm more like a star and a planet, where the star is forced to wobble in its dance while the planet swings in a large orbit. We call that balance point the center of mass, and its position is determined by the relative masses of the two objects. There's a kind of a cartoon, not to scale, to show you the geometry. This is Bugs Bunny, by the way, doing the square dance calling. That's why it's getting very violent. We think of the sun at the center of the solar system, but really it's orbiting in a swing dance with a bunch of dance partners. Jupiter is the most massive of those partners, but the Earth is one of those. And here is the dancing sun sped up over time, covering 30 years of its dance moves, with basically 9 unseen partners if we count Pluto as the dwarf planet. And so if you could measure those wobbles in the sky of a star, you could find out that the star has unseen dance partners. Here's a map of that. And the scale here in angle, 1/4 millionth of a degree.
Now you're home. Bow to your partner. Bow to the gin across the hall. And that is all.
There we go. Thank you, Buds. Brought us to this point. To see an angle that small is like basically taking a picture of a human hair, a single follicle of human hair, resolved. And so if you were to see that from a star about 30 light years above the solar system and the wobble of the sun's position, it's like being able to distinguish the width of a human hair on somebody's head 200 meters away. Twice as far away as this guy, 2 football fields away. We don't have that capability yet. Aliens might have it, if they're out there. I hope they're out there, but we don't. So, although planets and stars are in these swing dances, and we do want to detect the wobble, but we don't detect it in its position in the sky. We detect it in a different way. We take the light and split it up into a spectrum with a spectrograph. And here, this incandescent bulb in the cartoon is representing the light from the sun. And what they had to do was they had to go to the top of the tallest volcano in the world, the summit of Mauna Kea, 4,200 meters above sea level. And with a spectrograph, before the light from the star went into the spectrograph, they put a container, a transparent container of gas called hydrogen fluoride in front of it. Now this was a great idea, and I'll explain to you why. It's also a deadly idea because hydrogen fluoride, HF, is one of the most toxic substances known to humanity. A few parts per billion absorbed through the skin or breathed in will kill you. And they were working with this stuff at a place where the air pressure is half that of what we are breathing right now. Why were they willing to risk life and limb? Well, here's the spectrum of a star. This happens to be a red giant star, what we expect the sun will become in a few billion years. And there's a photographic version of the spectrum. There are those fingerprints, and there's a digital version as well. The star is known as Arcturus. You can actually see it, with the unaided eye from here on a clear, dark night. Even in Toronto, downtown Toronto, I think you'd be able to see Arcturus. It's bright enough. Well, by passing the starlight through this gas, they imposed the absorption lines of the gas. And that container wasn't moving with respect to the telescope or the instrument, so there's no Doppler shift. And so you're putting a ruler on every spectrum, the most precise ruler that anyone had ever come up with to measure the motions of stars. And Jeff Marcy, now at Berkeley, at the time at San Francisco State University, took that idea and adapted it to the more benign gas, iodine. And the reason why Gordon and Bruce hadn't used iodine is because it's a very complicated spectrum, and it had to wait for computational algorithms to allow us to deconvolve, to basically disentangle the spectrum of the star from the spectrum of this reference gas. But it worked. And these two guys, Michel Mayor, Didier Queloz, Swiss astronomers, in 1995 announced a planet orbiting the sun-like star 51 Pegasi, using the techniques that were pioneered right here in Canada. And there are the data, and they look very happy for having discovered this. The star, the planet, was a surprise. We nicknamed these hot Jupiters. It's a planet that's almost the mass of Jupiter, a gas giant, but it's orbiting 20 times closer to its sun than we are to ours. Nobody expected planets like that to be in orbits like that. Even my students in introductory classes at UBC think that's weird, and this is a quote from one of my students last term. "No way that can be a real planet. A gas giant so close to its star," he thought that I was pulling the class's leg. But no, these are real, and there are many of them, and as of this evening, 763 confirmed planets, and here's a little animation from Sylvain Korzenik at the Harvard Center for Astrophysics, illustrating the swing dance and the radial velocity curve of another system, Rho Corona Borealis, plus 2,300 candidates found through another technique called transits. So let me take you on a ride on an exoplanetary transit system. And I should point out, when you see the sign there that says way out, when an astronomer says way out, we mean way, way out. Let me explain what I mean by a transit. It's kind of like an eclipse, except it's when something passes in front of a star which isn't big enough to completely block it out. And so if you're lucky enough to see a planet whose orbit happens to be along your line of sight here on the Earth, and it passes in front of the star, we can't see the movie the way it looks here, but we can see, if we're careful enough, the change in the brightness of the star, the drop in light from the star as the planet blocks out a small chunk of its disk. You don't have to go outside of our solar system to see transits. They occur for the two planets closer to the sun than we are, Mercury and Venus. Most recent transits of Mercury in November 1999, May 2003. You're seeing there in that time-lapse movie below is actually ultraviolet images taken by a NASA satellite called TRACE, with the silhouette of Mercury just skimming past the edge of the sun. And Venus. The most recent transit of Venus occurred on the 8th of June, 2004. And I was in Much Hoole, England, near Preston in central Lancashire, where Jeremiah Horrocks, a young man, predicted when a transit would happen to Venus and observed it, the first human to observe a transit of Venus. And so many astronomers were gathered there, and we had a conference on the scientific importance of transits in and beyond our solar system. But what was really significant about it is because on the night of the day of June 7th, there wasn't a single human being alive who had ever witnessed a transit, because the last one had occurred in 1882. Now, the night before, I was in Preston at a pub, and a young woman caught my eye, and I went up and started chatting with her. And I said, you know, if you come back with me tomorrow, I'll be able to show you something that no living human being has ever seen. Turned out to be a very effective pickup line. Anita and I dated for 2 years, and we're still very good friends. So you never know where you're going to make those connections in science. Well, transits are fantastic for exoplanetary study. They're one-stop shopping, because they're the only way we can directly get the size of a planet relative to the size of its parent star. And these are data actually obtained with Canada's Space Telescope of one of these transits. And we get the true mass. With this Doppler wobble technique, the swing dance technique, we get only a lower limit on the mass. But if you know the orientation of the orbit, if the orbit takes the planet in front of the star, then you know the true mass by combining those Doppler measurements and the transit photometry. And these kinds of observations are literally rewriting the textbooks. Things that I'm telling my students in introductory astronomy classes today. We didn't even have the language for it much more than 5 years ago. And if you're going to rewrite something, you need a pen. Here are my pens. They're pens that draw what an astronomer would call light curves. Ultra-precise measurements of the brightnesses of stars and exoplanets and their interactions. And the first of these pens is Canada's first space telescope, as Colin mentioned in his introduction. MOST, designed, built, and operated at UBC. We're having babies, a Canadian-Austrian-Polish collaboration called Bright Constellation, Bright Target Explorer, and the first two Bright nanosats are due for launch on an Indian rocket, an East Indian rocket, later this year. The French joined us in space 3.5 years later with a mission called Corot. And finally, the latecomers to the party, nearly 7 years after Canada went into this terrain, the NASA Kepler mission, ExoEarth Hunter. And the Kepler mission is an incredible mission. It's doing that equivalent of the alien anthropologist doing a census of humans. It's doing the first real statistically meaningful census of exoplanets. And here's our galactic city, seen from sort of outside and above. Should point out, by the way, this is artwork by John Lomberg, who was a frequent collaborator and a close friend of Carl Sagan. And the volume of space that's being explored by the Kepler satellite is kind of like a rectangular cone, about 3,000 light years long, about 150,000 stars being searched for planets. Well, when we're talking about these space telescopes, I mean, the most famous space telescope to anybody on the street is this one, the Hubble Space Telescope. That's America's space telescope. Let me show you Canada's space telescope side by side. There it is, MOST. MOST stands for microvariability and oscillations of stars, microvariabilité et oscillations stellaires, perfect Canadian acronym, probably why we got funded by the federal government. But because of this comparison, we've nicknamed it the Hubble Space Telescope, as Colin pointed out. And it came out after we were in orbit that people realized that we had stolen elements of the design from another source, and so we now have to publicly acknowledge SpongeBob SquarePants. He's become our unofficial mascot. What MOST is a light meter in space. It doesn't take pictures in a conventional sense or spectra. What it does is it measures the changes in the brightnesses of stars. And it can see changes in starlight and their brightness as small as 1 part in a million, 1/10,000th of a percent. And that's me in my bunny suit in the clean room with the MOST satellite before it was launched. Now, astronomers have a hard time wrapping their heads around changes this small, and if astronomers do, you can bet that government bureaucrats that you're approaching for funding have this problem. So I had to come up with a way to explain it in a more human context. This is what I came up with. If you want to see a drop in brightness of only 1 part per million, go to New York City. And imagine looking at the Empire State Building. All the lights are on, all the office window shades are fully open. You can make the Empire State Building fainter, less luminous, by 1 part in a million, 1/10,000th of a percent, by having one person stand at one window and pull down one blind by 3 centimeters. And if you have them move that blind up and down by 3 centimeters, they'll make the Empire State Building oscillate with an amplitude of 1 part per million, peak to peak. And that's what MOST is capable of seeing. And that's also what the French Corot and the American Kepler missions are capable of seeing. It's a new frontier. We're used to thinking of capabilities like seeing at new wavelengths, seeing fainter things. But this is a new frontier in time and in light sensitivity that has really rewritten the textbooks. And so we've been joined by Corot and Kepler, and we'll soon be joined by our little bright constellation on this scientific frontier. So again, why do all of this? My 6th lesson is AstroPrimatology, how to get your 2 centigrades worth. Here's an artist's conception of exoplanets. We call them exoplanets, but come on. They're alien worlds. That's what normal people would call them. Alien worlds like Pandora, James Cameron's conception. That Pandora is, without a doubt, boring. Absolutely boring. Let me show you an exciting world. Not with an exciting name, unfortunately, HD 80606. James Cameron would do better than that. The star is one of a pair of stars like the sun, about 58 light years from us, one of our nearest neighbors in the galactic city, in the direction of the sky where you'd see the Big Dipper. Put things in perspective. Here is the Earth's orbit around the sun. It takes us 1 year, 365.25 days to go around the sun. Here is the orbit of HD 80606b. It has their very elliptical orbit, period of 112 days. It goes out almost as far as the Earth in our own solar system from the sun, and then swoops in over the surface of its parent star. And let's zoom in to the part where it's moving across what would be the orbit of Mercury in our own solar system. The way orbital dynamics work is that things move fastest when they're closest to the star. And so the distance from the star changes dramatically in only a few days. Each one of those little symbols representing the planet are a day apart in its orbit. It goes from the distance of Mercury to just above the surface of the star in a week, and then back again. That means that it receives a changing flux of starlight, of sunlight. The weather changes in a matter of hours. Now, I'm not talking about like here in Toronto. The weather can change from sunny to cloudy to rain to snow in a matter of hours. I'm talking about the weather and the entire planet changing together in a few hours. We are concerned about climate change, about a rise of 1 or 2 degrees Celsius across a century. That's nothing. HE 80606b, 400 degrees Celsius in a week. It would go up 400 Celsius and then drop back down. It's a climate roller coaster. Even science fiction writers didn't think about worlds like this. You know, we're finding things, we're going ahead of science fiction with science fact. And why should we care about this? Well, I can give you a weather forecast. Here is the forecast for today, 80606b. Today's high is 1400 degrees Celsius. Very high winds, kind of like today, here in Toronto. Clear, no clouds. But this is a very extreme system. So why should we care? Well, because if we're going to understand the interactions of climate with the sun and with other drivers, what you want to do is be able to experiment. You want to see all parts of parameter space. If you're testing something in physics or chemistry, often you want to test it to the breaking point. We don't want to test the Earth to the breaking point, but nature has provided us with other climates that are at what we would consider the breaking point in very extreme conditions. And we are going to be able to see how things respond under those conditions, and that's going to be able enable us to have models which will better reproduce how things happen in our climate under much less extreme conditions. So yes, Pandora is boring. It's just kind of a conventional Earth-like planet. But while I'm talking about cinema, here's a new course in Astro-Aquacinema Studies. Awareness through immersion. Where will Avatar 2 be set? To answer that question, first let me show you a cutaway of the Earth as you'd find it in the grade 7 science book in the BC curriculum. And we are finding SuperEarths, that their interior structure is probably not that different from what you'd see in a standard terrestrial geology textbook. But we're also finding things that may be aqua SuperEarths. And these models were first generated by a PhD student at Harvard, Diana Valencia, Canadian, Argentinian extraction, who was an undergraduate student right here at the University of Toronto and became a Carl Sagan Fellow. And Diana is one of these that's showing us what could be the interiors of these, and these two categories of sort of terra and aqua SuperEarths. And that puts things in a whole new perspective. We think of the Earth as being a very lush, wet world. You know, 3/4 of the surface covered by ocean. The volume of the ocean, about 1.4 billion cubic kilometers. That's a big number. Big numbers often don't mean anything to normal human beings. Even if you break it down and divide that by 7 billion, so that you say how much water would there be even if we didn't share it with the other life on Earth for each human being, that comes out to be about 200,000 cubic meters. Still, I mean, that's 80 Olympic swimming pools. But not all of that water is accessible to us or usable by us. And if you were to basically distill it down, pun intended, to the stuff that we could use per person, not counting plants, animals, insects, comes down to basically 1 swimming pool each. If you knew in your heart of hearts that all the water you would ever use in your whole life would fit in 1 swimming pool, you probably wouldn't pee in that pool. And that's the kind of message that these discoveries are helping us get. If you took all of the water on Earth and gathered it into a single sphere, the oceans, the ice caps, groundwater, lakes, rivers, moisture, water vapor in the atmosphere, you get a sphere about 1,400 kilometers across, and this is due to Adam Neiman. If you have an aqua super-Earth, this is the volume of water in the oceans, the same volume as the Earth. So if we look at the water budget for the Earth versus the potential water budget of an aqua super-Earth, about 700 times more, if those are common, and if there are aliens out there, maybe they feel sorry for us. Maybe they won't think of us as a wet, tropical planet. They'll think of our oceans as puddles. And gee, those poor humans, they have to splash around in puddles. And where will Avatar 2 be set? Well, James Cameron follows our research and the research in exoplanets, and he has already announced he loves oceans, and aqua super-Earths are literally a wet dream for James Cameron. And he has already announced that Avatar 2 will be set on an ocean super-Earth, another moon of that gas giant planet like Pandora. Now, my final lesson is in Barnum Disney Economics 202. The phrase, always leave them wanting more. By some accounts, it was said by P.T. Barnum. By other accounts, by Walt Disney. I know that I've already taxed your patience and time, but if you'll stick with me for a few more minutes, I won't leave you wanting more. I want to share with you a discovery that we made last year with Canada Space Telescope, a super-Earth that we found, but unlike any other super-Earth that's been known. We put a star in the direction of the constellation Cancer, 55 Cancri A, under the equivalent, the astronomical equivalent of a stakeout. We stared at it nearly continuously for 2 weeks in February, a little more than a year ago, to look for the signs of a planet, planet E. And those red bars are where a grad student at Harvard, Rebecca Dawson, had predicted there might be transits if she was right. Well, I've talked about this like an astronomical stakeout, but it's also like going to Vegas and playing the slot machines, because we didn't know if we had the right orbital period. Even if we did, geometrically there was only a 1 in 4 chance that the planet would pass in front of the star. And even if that happened, we didn't know whether the planet would be detectable by the MOST Space Telescope. Well, we did that on the right orbital period. We did beat those odds, and we hit the jackpot. If we fold that light curve, that record of brightness as a function of time, at the suspected period of the planet, this is what you see. We cornered our culprit in our stakeout. The dip in light as the planet passes in front of the star. Not a very deep dip, 1/25%. And if we could see it, this is what the transit would look like, compared to what aliens might see for a transit of the Earth or a transit of Jupiter. And the sizes of the stars are actually to scale if they were beside each other. The period of this planet, 17 hours and 41 minutes. That's its year. It goes around its star every 17 hours and 41 minutes. So if you lived on 55 Cancri E, to mark important dates and milestones, like the anniversary of New College or a wedding anniversary, you wouldn't use a calendar. You'd use a clock. Hey, it's 4:59, happy anniversary, honey. That's the way things would be on 55 Cancri E. And here is a sample of pretty much all of the planets for which we know their sizes and their masses. The ones in our solar system and the transiting exoplanets that we've studied sufficiently well. And those curves represent models of compositions, a pure iron world, a rocky world, a water world, and a gas giant. And if we zoom in to find where 55 Cancri is, you see it, and the error bars there, those things, that little cross, are the uncertainties in the parameters of that planet. Look at how big the uncertainties are in those other planets. The K stands for Kepler. Those are the things discovered by Kepler mission. And the C stands for Corot. So we're running with the big dogs here. And in fact, this planet is a bit of a mystery. I think of it as kind of a sumo wrestler of a planet in mass, but it's in the body of a super-Earth supermodel. It's the poster child for super-Earths. And here's just a list of some of the parameters, the numerical values that we know about this world and their uncertainties, and my collaborators on this. I don't think I know that many numbers about myself, let alone another planet. We could give this planet a passport, and you can't even see it. Now, Colin told you in his introduction of me that we were both science fiction geeks and fans at the time, and we were big fans of the classic Star Trek. And there was an episode of the original series called City on the Edge of Forever, in which Captain Kirk and Spock go back to the Earth in the 1930s. And Kirk starts chatting up a young woman, and at one point they're walking in the street. That's Joan Collins, by the way, a young Joan Collins playing Edith Keeler. And he points up to a star in the sky and he says, "See that star? Around that star there's a planet. And on that planet was born one of the greatest romantic poets in the universe." That was his pickup line. I can do that now. Not for evil pickup purposes, but I can point out to students, to people, and say, "See that star? Around that star, there's a super exotic super-Earth with a year only 18 hours long. And we've just finished re-observing that star. And we've done spectropolarimetry with it using a telescope on the summit of Mauna Kea, the same telescope that Gordon Walker and Bruce Campbell used for the initial searches for planets around other stars. And we're hoping to measure the magnetic field of another Earth-like planet for the first time. And so as time goes on, I'm going to be able to flesh out that story, going to be able to add more details to it. And yes, I can describe it to you, and you'll be able to close your eyes, and you're going to see another place. Not a place that we're going to be able to visit or escape to in the near future, but a place that's going to help us understand and appreciate where we do live. So when it comes to sustaining life on Earth, I would argue that the sky is not the limit. And before I finish, I just want to revisit that part of the sky and the new constellation, New College constellation. I want to point out that, of course, in Roman numerals, L is 50, and we're celebrating the 50th anniversary of New College. And I hope maybe, thanks to some of the things that are happening in this revolutionary time, that I and all of you will be back here 50 years from now, adding another Roman numeral to celebrate the centennial of New College. Thank you very much. I already know the answer to this question is no, but thank you so much for your patience tonight.